So our last topic in chapter 1 is going to be thinking about prime numbers. So this is something you're familiar with, and that definition at the top you probably know. So P is called a prime if first it has to be greater than 1, and its only divisors are 1 and itself. Okay, so prime numbers are the 2, 3, 5, 7, 11, dot, dot, dot. If a number is not prime, if it has factors other than 1 in itself, it's called composite. The number 1 is different. It's sometimes called a unit. It's also the multiplicative identity. Saying it's a unit means it has a multiplicative inverse, so in the set of integers. So it's different from primes and composites. It's sort of in its own category. But everything but 1, every natural number greater than 1, is either prime or composite. So the big result that, again, you're familiar with is this theorem. It's called the fundamental theorem of arithmetic. And it says every positive integer greater than 1 can be factored uniquely into a product of primes. And I have two things to talk about here. First is that word uniquely. What we really mean here is up to order. It's unique. So for example, if we thought about the number 18, I can factor that into a product of primes as 2 times 3 times 3. I could also write that as 3 times 2 times 3, but I don't want to think of that as different. So it's unique up to the order in which we write the primes, which we can change, of course. The second thing I want to say about this, just a side note, is that fundamental theorem language you may have seen before. So there are fundamental theorems all over different areas of mathematics, and they're sort of big results that tie together a lot of different things in whatever realm it is. So there's a fundamental theorem of calculus that talks about relationships between derivatives and integrals. There's a fundamental theorem of algebra, which talks about solutions to polynomials, and we'll see that one later in the course. This one, this factoring into a product of primes, is the fundamental theorem of arithmetic. All right, so primes are super important, and we know a lot about them, and there's a lot that we still don't know about them. So we're going to just look through a few facts that might be interesting to you, and then some of the things that we don't know also. So there are infinitely many of them is a fact about primes, and we're going to prove that very shortly. The second one, that there are arbitrarily large gaps between them, for homework. So that's going to be part of your next homework assignment. And what that means is I can find, if I want to find 10,000, two primes that are at least 10,000 apart, and two consecutive primes is what I really mean, that are at least 10,000 apart, I can do that. In other words, I can find 10,000 composite numbers in a row. So there are primes on either side of this stretch, but there are at least 10,000 numbers in a row that are not prime. So I can do that as big as I want. So I can find 1,000,000 composite numbers in a row. So two are at least 1,000,000 apart. And this is kind of an interesting idea, but it turns out to be not that hard to prove, and you're going to do it. All right, a couple more. So there is a prime between n and 2n for every integer. So if you take, as long as n is bigger than 1. So between 4 and 8, for example, there's a prime, and that's 7. The next one is called the prime number theorem, and roughly it says when n is big, the number of primes less than n can be approximated by this n over log n expression, which is pretty interesting. I'm going to put some pictures up if you want to read a little bit more about that. The last one says in any arithmetic sequence, so a sequence of the form a plus d, a plus 2d, dot, 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 as long as the GCD of a and d is 1, there are an infinite number of primes that show up in that sequence. Some unknowns about primes. One is the Goldbach conjecture, which says if you have an even number bigger than 4, the conjecture is that you can write it as a sum of two primes. The fact that this is a conjecture means nobody has proven it yet. However, we've done a whole lot of examples, right? Nobody has disproven it either. And so that means we have checked all the even numbers that we have been able to check, and they can be written as a sum of two primes. But no one's been able to prove whether or not this is true. So this is a really famous conjecture. So just as a couple examples, even number greater than 4. So if we take 6, we can write that as 3 plus 3. If we take 8, we can write that as 3 plus 5. If we took like 16, we could write it as 3 plus 13. So a whole lot of these even numbers have been checked, more than you can even think about. People don't know if it's true or not. We believe it's true, but nobody has been able to prove it. The next unknown is about twin primes. So twin primes are primes that are exactly 2 apart. So 11 and 13 are twin primes. 17 and 19 are twin primes. So they're primes that there's just one even composite number in between the two. And the conjecture is that there are an infinite number of twin primes. There are an infinite number of primes that are only 2. So this one, there was sort of a recent development, and again, I'll post a link to an article about this. A man in New Hampshire took a step toward proving this. It was something not like twin primes, but it was there are an infinite number of primes that are some other big number apart. All right, and then last, another thing that we don't know is whether there are always primes between n squared and n plus 1 squared. So this one, again, no one has been able to prove or disprove this. All right, so let's talk about that infinite number of primes. So we're going to try to prove that. So claim there are an infinite number of primes. All right, here's our proof. So this is a really clever little proof. It's a fun one to do. We're going to do a proof by contradiction. So what this means is if we want to prove that they're an infinite number, we're going to say, what if, so I'm going to use those instead. What if they're a finite number? So suppose there are only a finite number of primes. And we're going to give them names. So P1, P2, up to Pn. Okay, and so P1 is 2, P2 is 3, and then it kind of keeps going, list all the up till the last one. So Pn is the last prime. So we're going to assume that that's all the primes there are. And then what we're going to do is try to find something that doesn't make any sense. So in a proof by contradiction, you say, what if it's false? What if there are only a finite number of primes? And then we're going to try to come to a result that doesn't make sense. And so then we have to go back and say, then what I assumed must be wrong. So here's how we're going to do that. We're going to consider the number, let's call it x. It's going to be the product of all of those primes all the way up to Pn plus 1. So I'm going to take all the primes in existence, multiply them together, and add 1 to that. Okay? All right. Since x is larger than all primes, it must be composite. Okay? So it must have a prime factor. So if it's composite, it has to factor into a product of primes. So it has a prime factor, call it Q. Okay, so then we know that Q divides X, but also Q is in that set of primes P. So that means Q is actually equal to Pi for some I. And I can be more specific about that. For some I that's greater than or equal to 1 and less than or equal to n. Okay, so Q is one of our primes. It's one of the P1, P2, primes. All right, so now Q divides the product of all of these primes because it's one of them, right? So Q is on that list somewhere, and so that means Q divides the product of all of those things. But now we have two things that we can put together. So Q divides X and Q divides the product of all the primes. So q divides x minus the product of all the primes. But x was the product of all the primes plus 1. Okay, so putting this together, this means q divides 1. But q is prime, so q is greater than 1, which is a contradiction. Okay, and so what we said is q is a prime, but q divides 1, which makes no sense at all, so our assumption has to be wrong. So our assumption was false. Thus, there must be an infinite number of primes. All right, and that's our proof that there have to be an infinite number of primes. So in part of your homework, I'm going to give you kind of a false proof that seems like it works and see if you can figure out why it doesn't really work. And I'm also going to post for you a comic that does this proof in comic form and haiku form, which is kind of cute. So you can take a look at that also. So I want to make one note here. This is just a little bit of math culture for you. Remember, we did this as a proof by contradiction, right? And so we assumed that our claim was false, and then we reached a contradiction. Our contradiction here was that q had to be a prime, but it also had to divide 1, which doesn't make any sense. And so when we do these proofs by contradiction, they're kind of fun proofs to do. When we get to the contradiction, there are some symbols that we can use, and these are kind of fun symbols. So symbols for contradiction. A common one is two if-then arrows kind of pointing at each other. One that I always like to use is this sort of it looks a little bit like lightning striking, so I like that one. I learned it from Hungarian mathematicians, and I don't see it that often, but I think it's really fun to write, and I think that it's nice that it's like lightning. I like that one. Sometimes I've seen people do sort of an X with dots like this, and there are lots of other ones. So if you do a quick internet search for symbols for contradiction, you'll find whole threads about these things and what people's favorites are. So if you feel like wasting some time, go ahead and do that. One other side note, I always sort of thought these would be nice math tattoos. So if any of you ever want a math tattoo, I would recommend one of these. I do not have one, but I thought it would be kind of fun. So that's it. This wraps up chapter 1. So there'll be one more assignment for you to do, and then we'll be ready to move on to chapter 2.